Hello everyone and welcome to our channel, MooTechie. A special welcome to all the dairy technologists and students joining us. This is the first class in our new Unit 2 on mechanical separation in dairy engineering. We will be building on our knowledge of dairy processing by exploring the fundamental principles and equipment used to separate different components. We are beginning Unit 2, which focuses on mechanical separation. This unit covers the fundamentals involved in separation processes. The contents of this unit will include the fundamentals of separation, filtration, centrifugal separation, the cream separator, the bacteriophage, and the care and maintenance of this equipment. Mechanical separation is a broad category that encompasses several types of separation. These include liquid-solid separation, gas-solid separation, liquid-liquid separation, and solid-solid separation. The main methods of mechanical separation we will discuss are sedimentation, centrifugal separation, sieving, and filtration. These methods have many applications in the dairy industry. They are used for the separation of extraneous matter from milk. They are crucial for the separation of fat from milk to produce cream and skim milk. They are used to separate fine powder particles from the exhaust air of a spray dryer. And they are used for filtering moisture from various dairy products. Let's start with sedimentation. Sedimentation is the process of removing solid particles that are heavier than the liquid using gravity. A simple example you might have seen is the layer of cream that forms on top of milk when it is left to stand. In industry, this process is carried out in a sedimentation tank or clarifier. For sedimentation to occur, certain requirements must be met. There must be a liquid dispersion, which is a mixture of two or more phases, where one is continuous. The phases to be separated must not be soluble in each other. They must also have different densities. In milk, the milk serum or skim milk is the continuous phase. Fat is the dispersed liquid phase. And items like udder cells, pulverized straw, and hair make up the dispersed solid phase. A key concept is sedimentation velocity. A solid particle or liquid droplet moving through a viscous fluid medium under the influence of gravity will eventually attain a constant velocity. This is called the sedimentation velocity. We can calculate sedimentation and flotation velocity using Stokes' law. If a particle's density is lower than the fluid, it will float at a flotation velocity, denoted as V sub g. The factors in the equation are particle diameter, d, in meters, particle density, rho sub p, in kilograms per meter cubed, density of the continuous phase, rho sub L, in kilograms per meter cubed, viscosity of the continuous phase, eta, in kilograms per meter second, and gravitational acceleration g, which is 9.81 meters per second squared. Stokes' law states that V sub g equals d squared times the quantity rho sub p minus rho sub L divided by 18 times eta, all multiplied by g. This graph illustrates the flotation velocities of fat globules with different diameters, showing how smaller particles move more slowly according to the equation. Sedimentation can be done in batches using gravity. This diagram shows two sedimentation vessels, A and B, which hold the same volume but have different sedimentation distances, labeled H1, H2, and H3. The height of the vessel impacts how quickly separation occurs. For larger scale operations, continuous separation by gravity is used. This is often done in tanks containing horizontal or inclined baffle plates, which increase the effective settling area. The inlet stream enters, and separated outlets allow for the continuous removal of different phases. This slide shows a vessel designed for the continuous separation of a solid phase and two liquid phases. It has an inlet labeled B. B1 is the overflow outlet for the light liquid. B2 is a baffle that prevents the lighter liquid from leaving through the outlet meant for the heavier liquid. Now we focus specifically on liquid-solid separations. A common piece of equipment for this is clarifiers, also known as sedimentation or settling tanks. These are large tanks where water is made to flow very slowly to promote the sedimentation of particles. There are several types, including rectangular clarifiers, circular clarifiers, and tilted plate clarifiers. This is a diagram of a rectangular clarifier. It shows the influent entering, going through a rapid mix chamber and a distribution channel into the clarifier basin. The clarified effluent is collected in a channel and sludge is removed from the bottom. Here we see a photograph of a rectangular clarifier in operation. Next we look at circular clarifiers. The diagram labels key parts: the bridge and walkway, inlet well, drive assembly, scum baffle, influent pipe, effluent launder, sludge rake arms, sludge well, scum box with beach plate, scum outlet, and sludge discharge. This slide contains a photograph of a large circular clarifier system. Another type is the tilted plate clarifier, also known as a lamella clarifier. The diagram shows flash mix and flocculation tanks feeding into the main unit. It has modular laminar plates, an access hatch, a baffle, and outlets for clarified effluent and thickened sludge. This slide provides a detailed view of the construction and function of a lamella separator, showing how the angled plates provide a large surface area for settling in a compact space. Now we move from gravity-based separation to centrifugal separation. Centrifugal separation is essentially sedimentation amplified by centrifugal force. It greatly increases the rate of sedimentation. A field of centrifugal force is generated when a vessel filled with liquid is spun, creating a centrifugal acceleration, denoted as A. Unlike constant gravity, this centrifugal acceleration is not constant. The centrifugal acceleration increases with the distance from the axis of rotation, which is the radius r, and with the speed of rotation, expressed as angular velocity omega. The formula is A equals r times omega squared. If we substitute this centrifugal acceleration for g in the Stokes' law equation, we get the sedimentation velocity in a centrifuge. V sub c equals d squared times the quantity rho sub p minus rho sub l divided by 18 times eta, all multiplied by r times omega squared. Centrifugal separators fall into two main categories. Cyclones are devices where the fluid moves through a fixed device to create separation. Centrifuges are systems where the entire apparatus moves to create the centrifugal force. Centrifuges have many uses in dairies. They are used for separation, such as separating fat and skim milk. They are used for clarification, to remove dirt and cellular debris. They are used for standardization, which is the removal of fat to adjust its content to a desirable level. A special process called bacterifugation removes bacterial cells. They can also be used for centrifugal evaporation and for solid concentration, like in the recovery of whey protein. We now shift to a different type of separation, gas-solid separations. This is often referred to as dust collection, which is concerned with the removal or collection of solid particles dispersed in gases. There are several important purposes for dust collection. It is used for air pollution control. It reduces equipment maintenance. It eliminates safety or health hazards. It improves product quality. It allows for the collection of powdered products. And it enables the recovery of a valuable product. It is often necessary to measure the concentrations and characteristics of dust. This is needed to determine if control measures are required, to establish compliance with legal requirements, to obtain information for designing a collector, and to determine the performance of an existing collector. The basic operations of dust collection involve a few key steps. First, separating the gas-borne particles from the gas stream by depositing them on a collecting surface. This requires applying a force that produces differential motion of the particle relative to the gas and allowing sufficient gas retention time for the particle to migrate to the surface. The process also involves retaining the deposit on the surface and finally removing the deposit from the surface for recovery or disposal. The principal mechanisms for aerosol deposition include gravitational deposition, flow line interception, inertial deposition, diffusional deposition, and electrostatic deposition. One common device for gas-solid separation is the cyclone separator. It is used for fine particle or dust collection, separating solids from gas. The separation relies on the terminal velocity or settling velocity of particles, which can be described by Stokes' law. The equation is V sub g equals d squared times the quantity rho sub p minus rho sub l divided by 18 times eta. The clean gas exits out the top, while the separated dust is collected at the bottom. This slide shows a diagram of a cyclone separator. Another type of device is the Venturi scrubber, which is a type of particulate scrubber. These can be high-energy or low-energy devices and are known for being simple and flexible. Scrubbing water is introduced into the gas stream. The particulate matter is captured by the water droplets. The clean gas then exits, and the slurry containing the dust is separated out. This slide contains an image of a Venturi scrubber system. Thank you for joining this first class on mechanical separation. We covered the core concepts of sedimentation and centrifugal force, and we introduced the various types of equipment used to separate liquids, solids, and gases in the dairy industry. This foundation is essential for understanding the more specific machines we will discuss in the next class. Thank you. See you in the next class.